Hey folks, I hope you're enjoying the summit so far. My name's Tern and I'm the VP of Data at Quix, which is a Python streaming data technology company. Thank you very much for joining this talk. It's called Enabling Low Latency Fraud Detection with Real-Time Feature Engineering. So I'll aim to have these questions answered for you today in the next 15 minutes. What is real-time feature engineering? How can you build it out? And how you can achieve low latency? So first, a quick definition of feature engineering. You probably know this already, but features are properties that provide machine learning models with predictive power. They're inputs for models during training and inference, and they're sometimes derived directly from the data, and sometimes they're computed. Let's first understand the traditional type of feature engineering first, which is batch feature engineering. You have data in this pipeline that is processed and written as historical labeled data to a data store. This is read by a feature processor to extract and compute features, and it's written to an offline feature store. These are optimized for high volumes of data, and this is what's needed for model training. You need lots of data. So you're probably familiar with this kind of pipeline, and you might be using a database like PostgreSQL or MySQL to store your labeled data, and you might be using another sort of database or cache like Redis for your feature store. And in your workplace, the processing engine of choice could be anything. The talk of the town is Flink, and you might be using something from the same era like Spark. Feature stores are really good because they decouple feature engineering from models. Historically, when that was coupled, you'd have different variants of logic and computation, which resulted in different variants of features being used as inputs to model training. And then again, you get some variation again during model inference, where there would be different features used that didn't match the features used during training. And this decoupling ensures that there's a central place for features. Like Jim mentioned something about that famous quote about indirection, having another layer of indirection, really good in this case. Let's take a look at the data with the example of fraud detection for credit card transactions. I've taken these example records from Hopsworks synthetic data generator. And if you look at their transaction there on the left, you can see that there's a natural key there. You've got a credit card number, and there's a purchase in a restaurant or a cafeteria in a city in the US. And now if you look on the right at that transaction, you can see that less than 24 hours later, there's a cash withdrawal in a city in Indonesia. So this is a really good, believable example of a transaction that's been labeled as fraudulent. But for the most part, if you take a look at these transactions in isolation, it's really difficult to predict any sort of fraud. So typically, you would enrich this data by joining it with other data, such as profile data, which helps bring better context to the transactions. So there on the right there, you can see some profile data has come in. There's the natural key again, the credit card number. And in a batch pipeline, this transaction data with labels would be built up over time. You'd also update that profile data as it changes slowly over time. It's considered a slowly changing dimension. You'd use this data to compute the features and train a model to achieve your desired accuracy. And here are some of the features that you could compute. Spoiler, a lot of the useful computed features are aggregations. And some of the features, such as the aggregations over longer periods, for example, a week or a month, you may have to process many, many data points, and this can be really time-consuming to compute. So that's where you might be pre-computing them and saving them to a feature store. With real-time feature engineering, you have a pipeline that serves real-time inferences. It must run with low latency entirely end-to-end to ensure that the ML model is supplied with the latest features. The data ingestion, the feature engineering, and the feature retrieval needs to happen in real time or near real time. The same example I gave for the transactions data would be flowing through, but of course in this pipeline, the ML model would need to retrieve the features so that it can predict whether a transaction is fraudulent. It may well need to compute features on the fly. For example, if there's a scoring rule that needs to be applied based on current location. The challenging part in a real-time pipeline is that feature engineering part. The other parts like the data ingestion, the feature store and the retrieval, that's largely figured out. So I think teams are still having this feature engineering part of the pipeline be a real challenge. And from what I've seen in customers and in open source, teams tend to prioritize two things here. So the first thing is low latency feature computation. And the second thing is a good developer experience when you're building out that logic. Let's take a practical example and fill in some of the technologies here that we're going to use. So the first one there is Quix Streams. It's a real-time open source data engineering framework. It has a sources and sinks API to very easily connect to various data sources and build out your own custom connectors. And if you're wondering why the logo looks like a Python, it's because it's pure Python. We have there at the bottom there, Apache Kafka. It's a streaming message transport or broker. And the beauty of Kafka is it's a true distributed system that's built to scale for high throughput whilst keeping low millisecond style latency. It's also designed with guarantees around message delivery, reliability, and durability, meaning that you don't get any data loss. And Kafka, it was written in Java, and though it has clients in languages like Python, they tend to be very simple producer consumer types of applications that you can build. They give you the low level building blocks, but it's up to you as the developer to build out the high level abstractions. And for feature engineering, you require abstractions such as window operations and state management. So you need to reach for a more mature library that can handle these sort of common tasks. And that's really why Quix Streams is a good fit in the data and the AI ecosystem. And then on the right, you've got HopsWorks, which you probably know about by now. It's a Lakehouse platform with a feature store, and it solves many of the challenges when building out these sort of complex data systems. So considering the transaction and the profile data together, this is how a pipeline could be designed. So at the bottom, you've got the slowly changing profile data. So whenever a user updates their profile, an event is generated and it's streamed into a topic called profiles raw. It's consumed in real time by a profile feature processor that will transform it to generate the features and then store them in the online feature store. And at the top, you've got the fast flowing transaction data. And this would originate from payment systems and terminals, and it's produced to a Kafka topic called transactions raw. It's consumed in real time by the transaction feature processor, and then it will enrich the transaction data with profile data. Again, it may go back to the feature store to fetch the features, and then from there, it will compute new features. These new features are written back to the feature store and will keep that feature store up to date so that when the ML model is requested to make a prediction, it can read the data with the confidence that it will be fresh. For the longest time, you weren't really able to enable low latency through technology choices without suffering some sort of pain. A lot of these technologies like Kafka require complex infrastructure, and the companies, some of whom are on the schedule here, like Uber and Pinterest and Airbnb, these companies, they tend to deploy these big platforms and have dedicated platform teams to look after them. That's changed a lot in the last few years with lots of new projects and vendors coming in aiming to make real-time data processing accessible for the next generation of data engineers and data scientists. Note that you can't use a traditional database to achieve the high throughput and low latency that's provided by stream processing and feature stores. These are technologies that were built from the ground up with these kind of critical use cases in mind. So going through the list there, if you're choosing streaming data, you've got to choose an online feature store. This will enable you have consistency between your offline and your online workloads, and that you have fast retrieval. You've got your streaming message broker, so you can choose from something that has the best ones we found out there are those that implement the Kafka API, so Apache Kafka itself, Redpanda, Pulsar, and use stream processing for feature engineering. If you're already using Spark for your batch workloads, I recommend, first of all, trying out Spark structured streaming. You've also got Flink, and you have Quix Streams as well for those who are more Python-centric. So Kafka is a distributed system and it uses partitions. So we know that it can scale horizontally and it can scale out to deal with higher throughput and higher volumes. But what are the other characteristics of its system design that makes it fast? And it's really down to two approaches. So you've got sequential I/O and you've got the zero copy principle. So first of all, sequential I/O. So you've got records in Kafka, and they have ordering guarantees. And this is facilitated by Kafka's design, which is to store data as an append-only log. So you've got data that is organized as contiguous blocks of memory, as in they are stored like kind of physically next to each other. You've got modern drives and solid state disks, which are optimized for sequential I/O as well, rather than random I/O. And you can contrast that with kind of like the grid there on the left with random I/O. This is more characteristic of your relational databases. They're optimized for random access because you can never really predict what a user wants to query in that database. So they're optimized for that. Another side note is that Kafka was launched around 13 years ago. It's a long time, it's a lifetime in the streaming world. And during a time of hard disks with split with those kind of physical spinning platters of magnetic disk, it meant that sequential, like implementing something sequential meant that there was no disk seek time. So those platters didn't really need to spin much. So what are the implications in our current era with solid state disk drives? I recommend following the link in that image credit to find out more. Zero copy principle. So this refers to the copying of data between the kernel and the application context. It doesn't mean making zero copies. What it means is minimizing the number of copies between those two worlds. So how it actually works in practice is the Kafka consumers will read the topic data directly from the log file using DMA, which is direct memory access. So that saves on some time and keeps the latency low. Unfortunately, it doesn't apply when encryption like SSL and TLS is used because you have to hit the compute layer so that you can encrypt and decrypt. So zero copy principle is one of those things that contributes to low latency, but not as much as sequential I/O. The last few slides, I'll talk a bit about the technologies there that I mentioned, like Quix Streams. So Quix Streams is an open source pure Python framework. It introduced this concept of streaming data frames. And some of you out there may be familiar with data frames from libraries like Pandas and Spark. It's a very convenient way to create tabular representations of data and manipulate it that way. You can see in the code that there's some simple setup there to connect to a Kafka broker and set up the topics. You create a streaming data frame from that input topic. And what it is it's a data frame that continuously refreshes in real time as soon as new data arrives. You can see that we access the properties as columns in a table, and this makes for a really convenient API for extracting features like via doing projections. And we designed the functions to be named and to behave very similarly to pandas. So they're almost interchangeable if you're familiar with pandas. We've got stateful operations. For example, when you need to maintain a count of credit card transactions, you have access to a higher level state object, and you would use it like a dictionary or a hash. And its updates are backed by a local RocksDB store, and it's also backed remotely to an internal Kafka topic. So this means that in the event of an application failure, you don't have data loss, and you can maintain message semantics such as exactly once processing. There are other stateful functions, such as window functions available. You use them, for example, when you want to compute a count for the number of credit card transactions in 24 hours. You use them for any sort of aggregation over a time window. And here you can see there's a tumbling window of 10 minutes that has a 10-second grace period. You generally apply a grace period to deal with any late arriving events. You get late arriving events in kind of like the event-driven in Kafka world because sometimes events are generated, they're slow to be generated. You've got things like network issues. So we always apply a grace period to make sure that they count towards that window. You can see there that we are using a sum aggregation function, but you can supply your own custom aggregation because we enable you to supply an initializer and a reducing function. And this one's my last slide. This is about Quix Cloud. So Quix Streams applications don't require any server-side software. They run anywhere that Python is installed. And the approach that we take is to deploy them as Docker containers. So the Quix platform is a fully managed platform that connects to your Git repositories. It handles CI/CD to build your applications as containers and deploy them using Kubernetes. So all of that's fully managed and abstracted away, leaving you to be able to focus on building out your pipelines without worrying about infrastructure. So the workflow here is to use the Quix CLI to set up your project, develop and test your pipelines locally using Docker Compose, and then deploy them to Quix Cloud. It's been tried and tested by a few of our customers, some of whom are Formula One racing teams. So please do try it out. And feel free to connect with me. So thank you very much for coming to my talk. You can find me on Slack as well. So I invite you to come along, and the whole team's there to support you in your journey. So thank you very much.